Oh.
I don't
We
think
can take a field trip, guys.
We could, yeah. Not today.
All
All right. Increasing, decreasing first derivative test all wrapped up into one big fun slideshow. Yeehaw! Lot going on. However, I will say the one benefit we got going for us is that that's got thrown on the floor. Stay there. Is that it's very algorithmic. Okay. So we're going to figure out where a function is increasing and decreasing, meaning going up or coming down. We're going to talk about the first derivative test. If there's a first derivative test, logic would dictate that there is a second derivative test, and if there's a second derivative test, logic would dictate. Yeah, there's no third.
Oh.
And then your goal for today is to compliment two strangers. It should say compliment two strangers today without being creepy. Okay.
But since it doesn't.
Excellent point. As Oliver just brought up, since it doesn't say that, feel free to be creepy. What's that? Well, don't you know everyone in this? We're not so right now. All right. Here's the edge of speak. We've got two functions, or sorry, we have a function and it's increasing if we have two numbers on that function, x1 and y1, and x1 is less than x2. Therefore, f of x1 would be less than f of x2. Okay, what does that mean in English? You got x1 on the left of x2. That's your hypothesis of the starting part of it. If the y value of x1 is lower than the y value of x2, the function is increasing, going up, getting larger, creating a hill versus a valley. The y value is larger. You got it. It's decreasing if the opposite is true. x1 is still on the left, x2 is on the right. Stand up, sit down, fight, fight, fight. If the y value of x1 is greater than the y value of x2, then it's going down, decreasing, getting smaller. Fairly easy concept. Don't just say it to amuse me. Pregunta.
Is there a way to, like, do you have to have the graph?
You don't have to do anything, Jimmy. This is America. Fight the power, right?
Is it necessary to have the graph to tell if it's increasing or decreasing?
Nope.
Because you can just look at the end.
I'm going to show you some mathemagic.
Oh, Jesus.
Okay, I said that already. If it's going up, it's increasing. If it's going down, it's decreasing. We good? No, you're not good? You want me to get the dog?
Yeah.
Okay.
That would be really
Can you like
cool.
actually get some dog shit? Like, do you have the power to just like?
You know what would make it better? You know what would make everything better?
I brought the dog up here before. The problem is they don't trust me with the dog. So if I ask for the dog to come up here, I can't just go get the dog and bring the dog up here.
You have to come with.
Mr. Berg or Dr. Thornton has to come with the dog because I'm too stupid to handle the dog.
Well, I'm fine with it. I'm fine with it. We're gonna get a dog.
You trade off one of them for a dog?
No, I'm still.
Or you would deal with them
Yes.
for the benefit of getting a dog.
Exactly.
Is anybody allergic to dogs?
Wow.
Are you really?
I'm the one who asked for the dog.
I mean,
corner. It's okay.
if I
You
said
have-
it,
put 'em in a
they're-
box.
They're non-allergenic. They're a thing.
Does somebody need to explain to Greg about the whole making thing? I'm not really comfortable nor qualified to do that.
Come over to Walmart. Non-allergenic dogs.
Hey, where's the non-allergenic dog eye? You guys make those here?
It's almost him.
Okay, so how do we do? I don't know why I'm laughing, it's not that funny, it's just cracking me up. How do we do this mathematically? It's real simple. We're going to take the derivative and we're going to test the derivative. That's why it's called the first derivative test. Test the derivative. If the derivative is positive, the function is increasing. If the derivative is negative, it's decreasing. If it's 0, we've talked about that already, right? What happens when the derivative is equal to 0? Cricket. Cricket. Yeah. It's a hill or a valley. Max or min. Oh, sorry, too fast?
Yeah.
Okay. Again, with a lot of this stuff, when it's in calculus speak, if it doesn't make any sense to you, translate it into something that works for you. Just copying things down blindly doesn't necessarily solve the problem. It's got to be in a verbiage that you can comprehend. All right, here we go. First example. Where's that bad boy increasing and decreasing? What do I do first? Find the derivative. Got to find the critical numbers first after we find the derivative. So in order to find the critical numbers, we need to find the derivative. So it's a, chicken and an egg type thing. Well, no, it's not really. Chicken and egg, you can go, which came first. This is, derivative comes first. Always. And so it's just pretty much a chicken. No egg. I chose a nice easy function. Take the derivative, set it equal to 0. Where are the critical numbers? Number / numbers.
X equals 0,
Okay. Is she right? 0 and 1? Hot diggity. So what does that mean? What could possibly happen at 0 and or 1?
Max or min?
Could be a max or min. Do we know? But I can show you how to find out. Okie dokie. Here's how we're going to organize all our data. We have this little thing called, we did that. Okay, 0 and 1. Good. We're good to go. We have this little thing called a first derivative number line. So you're going to draw a number line. It has arrowheads on it. And this is very important. Next to that number line, you're going to write f prime. If you're doing function h, then you would write h prime. It's easy to forget that, but it's extremely important because later we'll be looking at second derivative number lines, and you need to be able to distinguish between the two. So what I know is I have some critical numbers, 0 and 1. Next step, graph those on the number line. You might want to get in the habit of using dots and circles, because sometimes it'll include the points, sometimes it won't. I chose an easy function if we go back. Can x be 0 and 1? Yeah, no problem. Okay, because remember, critical numbers come from where the derivative is equal to 0 and where the derivative is undefined. So if you got that business going on, you might want to turn these into dots and circles so you know if you're including it or not. Then we got to test some regions. Sid, what's a good number to the left of 0 to test?
-1.
Outstanding. -1. Give me another example.
-10.
-10. One more just for giggles to make sure we all understand what you're talking about.
Negative infinity.
Wow, that kind of derailed pretty quickly. I mean, everything was going great and then you just right off the road into the ditch. I think I can work with that though. I think I can work with that. This is the first derivative number line. So when we're testing regions, where do you think you're going to plug those numbers into? You dog, you. First derivative. So let's come back over here. If I put, what'd you say? -1, -10, and -infinity.
Yeah.
If I put -1, you know what, I'm not even going to look at this monster. I'm going to look at this puppy. Because all I care about is whether it's positive or negative. I don't care about the value because he can pick any number to the left of 0. So let's put -1 in there. If I put -1 in there, I get 3 times a negative number times a negative number. What's a positive times a negative times a negative? positive. Good. Sid, back to you. I'm not going to address the negative infinity right now. I don't have time. I need a number between 0 and 1. What would you prefer? Half. Beautiful. Put in a half. Well, that's positive. That'd be positive. A half minus 1 is negative. A positive times a negative is negative. Sid?
Yeah.
I need a number to the right of 1.
10.
10.
Yeah.
You want to go with that infinity gunk again? You're going to go with 10.
Yeah, 10.
10.
10.
You sure you don't want to use infinity?
Not yet.
Come on, let's use infinity.
Oh, infinity.
Infinity.
Yeah.
All right, good. So I put positive infinity in here. Is it positive or negative? Positive. If I take infinity minus 1, is it positive or negative? Positive times a positive times a positive is positive. Okay, so now we've tested our regions. And we can add that to our number line. Okay, so there's our critical numbers. And at the bottom, below the number line, I'm putting a plus and a minus there. As we go through more of these problems and they get more complicated, I'll show you some other ways to test regions. Great question. I was just going to get to that. Here's question. What's up with the arrows? Yeah, the arrows are showing whether the function is increasing or decreasing. So if the region that you're talking about is positive, you have an arrow going up to the right. If it's negative, it's going down. So, yes, sir.
But if it were, are we gonna ever have it where it's a closed interval?
Yeah,
So then that's when we have to actually test the numbers too.
maybe. You could.
I'm gonna put the arrows at every time.
Yeah. Yeah. So every time you're going to draw your number line, plot your critical numbers, include the f prime, tell me if it's positive or negative across the bottom, draw the arrows across the top. The other thing the arrows do for you is it gives you kind of an idea of the general shape of the curve. Because remember, we're starting with a cubic here. What do cubics look like? Well, they kind of look like this. Without spending too much time talking about it, because we're going to get to it later, what do you think is true about the point 0? Why? Okay, what does that mean?
Like it's increasing.
That's not going to help
It's
the people that are watching the video.
It's increasing and then it's decreasing
So why would that make it a max?
because the other side's decreasing.
Well, forget about this. What about, just talk about that. Why is that a max then if it's increasing then decreasing?
Because it'll be the highest value.
Does that seem like a silly, obvious question? If it's increasing and then turns to decreasing, why is it a max? Walking up a hill, if you go up the hill and then you start to go down the hill, you've got to hit the peak somewhere. Whose theorem is that? Rolle's theorem. Good. And what does it tell you might be true about 1? It would be a min, yeah. We'll get to that later. Right now we're just focusing on increasing and decreasing. Any problems? And so you see what I mean by this being algorithmic. What did I do? I took the derivative, I found the critical numbers, I plotted the critical numbers, I tested regions, finished my first derivative number line. Now I know where it's increasing, I know where it's decreasing. Your increasing and decreasing should be given in interval notation. When I do interval notation for this, am I going to include 0? Is 0 a parentheses or a bracket? I got both answers, parentheses or bracket, which one?
Parentheses.
When I get to the top of the hill, am I increasing or decreasing? What'd you say, Kate?
Yes.
Neither. So should I not include 0?
Yeah, you should not be.
Yes, I should not include 0. So parentheses at 0.
Yeah.
Okay. Everybody agree with that? The problem is either one is correct. And so you get a bunch of calc teachers to argue. They'll argue about it all day. My personal opinion is you don't include the critical numbers there. Because when you're at the top of the hill, you're neither increasing nor decreasing. But some would argue that you include it, yeah, but whatever. Now we get on to the first derivative test. So what's the first? The first derivative test isn't what we did. We're going to use that number line for the first derivative test. The first derivative test explains what you already told me, and that is that 0 is a maximum and 1 is a minimum. And so here's a picture of our graph, and you can see that 0 is a relative max, and 1, because its scale is not right, 1 is a relative minimum. So anytime you've got a function where it's increasing and then decreasing, you'll get a relative max. Anytime you have a function that's decreasing then increasing, you'll have a relative min. And now we're focusing on relatives, not absolutes. That's a different monster. The College Board is really big on writing. They want you to write sentences about stuff. So we're going to include a little sentence here that says, well, first of all, there's a first derivative test. Okay, so let me go through. You know this already. So if you want to copy it down, that's fine, but you don't really have to because you know this. You find your critical numbers first. Where do the critical numbers come from? They come from setting the derivative equal to 0 or where the derivative is undefined. If it goes from positive to negative, okay, positive increasing to negative decreasing, it's going to be a relative max. If it goes from negative decreasing to positive increasing, you have a relative min. And then if it doesn't change, then it's not an extrema. And you will see functions where it goes from increasing to increasing because something weird happens at that point, but it doesn't stop increasing. We'll see some of those. So not all critical points will generate a relative maximum, but all the relative maxima will be critical points. We talked about that a long time ago. If it goes up, then comes down, it's a max. If it goes down, then comes up, it's a min. Hills and valleys, max and mins. Okay, so we're going to find the relative extrema using the first derivative test. The process that we just went through is exactly what we're going to use to do this, except we have to add a little twist at the end for the first derivative test. So step number 1, take the derivative, go ahead. Take the derivative, find the critical numbers first, please. Derivataive.
Derivataive.
It's the Gaelic Derivataive. Ah, sure, you know, you're taking the derivataive. Find the relative extreme of the function. All right, so you find your critical numbers, then what do? Make a number line. Label that number line F prime, because we're using the function F. Decide if they should be solid dots or open circles. What should they be in this case? Solid dots. Good, solid dots, because it's a polynomial. Test some regions. So let's see what I got here for solutions. Okay. First, did you get those critical numbers? Good. The following seems like a silly statement, but it happens all the time. Please be sure that you plot your critical numbers accurately on the number line. -5 turds should be to the left of 1, right?
Yes.
Did you not all know that? Okay, good. Thank you, Alex. That's a big jump. So I plotted the 2 points, tested some regions. Well, what are you going to pick over there? When you plug back into the function, you probably want to plug into this factored form because that'll make your life easy. So I need a number to the left of negative 5/3. So maybe negative 10. If I put negative 10 in here, 3x plus 5 is negative. I put negative 10 in here, I get a negative. Negative times a negative is positive. Done. What's a good number to plug in between negative 5/3 and 1? 0. Oh, 0 is good. So if I plug in 0 there, I get a positive times a negative. Negative. Big honking number, 3,000. Positive times a positive, positive. And it leads us to that mess. And as we talked about in the previous example, then we know 5/3 is a max, and we know 1 is a min. It would be nice if we could then just say, oh yeah, a max occurs at negative 5/3, and a min occurs at 1, but it's a little more complicated than that. However, before I move on, let me make a distinction. You will see problems ask you different questions. What point represents a maximum? What is the x value of the maximum? What is the value of the maximum? Sometimes they'll be asking for the point, sometimes they'll be asking for the x value, sometimes they'll be asking for the y value. You just have to be cognizant of what it's asking you. Okay, so this is College Board likes you to write, so you're going to end up writing these kinds of sentences. And it will look something just like that. What do we have? A max or a min? Where does it happen? Why is that a max or a min? Okay. We've got a relative min occurring at x equals 1 because f prime changes from negative to positive. Not increasing, decreasing, we're just talking about the derivative. The derivative is changing from negative to positive. The other one would then just be the opposite. Relative max occurs at x equals negative 5/3 because f prime changes from negative to positive. You're going to write this every single time you find relative max and mins. So you burn that into your brain because they're going to be looking for that kind of sentence. That also satisfies the question, justify your answer. This would be your justification. That's why it's a max or a min. Any problems? Make sense? Okay. Take the derivative, find the critical numbers, put them on a number line, label that number line, test regions, summarize with a statement. Life is good. All right, let's do one more. I don't know. Oh yeah, I know that. Okay, so I'm doing this. What do I need to do to find the derivative? And product rule. Okay, so x to the 1/3 times negative 1 plus 1/3 x to the negative 2/3 times 8 minus x. I'm going to go through this quickly so that we can get done and you can get some cookies and Capri Sun because it wouldn't want anybody to feel deprived. That's a sum. I don't want a sum, I want a product. What am I going to factor out? X to the negative 2/3. When I factor out an x to the negative 2/3 out of x to the 1/3, I'll leave an x behind, but there's also a minus sign, so I'll get a negative x. I take out an x to the negative 2/3, that's out in front. I'm left with a plus 8/3 minus 1/3 x. Two critical numbers. Okay, now we set it equal to 0, solve for critical numbers. Critical numbers. X equals 0, that comes from that one. And then this guy. Well, what makes that guy equal to 0? That's negative 4/3 x plus 8/3 is equal to 0. X is 2. Yes. How'd I do that? Am I really good with fractions?
Yes.
No, I cheated. Multiplied everything by 3. So then I get negative 4x plus 8 equals 0, so therefore x has to be equal to 2. Come over here. This is an f prime number line. I'm plotting 0, and I'm plotting 2. And I'm going to come back to this guy to plug in. The derivative. Because it's a first derivative number line, so you're plugging into the derivative. So let's plug in negative 10. If I plug negative 10 into this function, this one I would get a positive value. What happens when I plug negative 10 into x to the negative 2/3? What can you tell me about x to the negative 2/3? Say again? It is a fraction. Anything else? Okay, these are the things that'll make your life a little bitty.
So less than 1.
Not necessarily. Oh, for negative 10? Yeah, but I'm talking in generalities. What's true about x to the negative 2/3? Hmm? It's always positive. Because it's raised to the second power. So regardless of what you put in there, you're going to square it, and it's going to be positive. So I don't have to plug in anything for here. I know it's going to be a positive. So for negative 10, I get a positive times a positive, which makes this positive. What's a good number to plug in here? 1. So if I take a 1 in here, I get negative 4/3 plus 8/3. Positive or negative? Positive times a positive is positive. Increasing, increasing. Put in 10. If I put in 10, it's going to be a positive times a negative, and that's a negative. What can you tell me about 0? Good. It's neither a max nor a min. It's just something weird. What's going to happen later as we move through the chapter is you're going to be graphing these eventually, and you'll be able to tell me exactly why it's weird at 0. What can you tell me about 2? Maximum. A relative max occurs at x equals 2 because f prime changes from positive to negative. You can cheat a little bit and abbreviate positive and negative instead of writing out those words.
Would it also be an absolute max?
It probably would, but I'm not 100% sure. More than likely, the function does something weird, hits that max, and then descends down into nothingness because there's nothing over there except it continues to decrease. But you're not going to be asked that question in that scenario because absolute max problem and min problems always come in when you got endpoints because you're going to look at it in an interval. Okay. By the way, this is a unit circle cake that somebody actually brought in for Treat Tuesday a couple years ago. It's a little hard to see, but there's the pi over there, pi over 2, 0. Way too much free time. All right, get some cookies and Capri Sun.
Don't touch me. Don't touch me. Because she's what you're not.